So today's topic is about chemical composition of biomass and also a few slides about reactions related to this type of molecules that can be found, or functional groups that can be found in in biomass. And this small list has been taken from the course book. And generally, if you take a look at biomass, like in the picture, that there are some leaves and grass and trees, woody material, and also if you think about fruits, berries, vegetables, and such kind of biomass. So it's a mixture of it's not just one single chemical, but it's always a mixture of different molecules. And also, like in this, so it's mentioned that it's a dry weight. So of course biomass is quite rich in water or humidity. So if you take a fresh piece of wood, it can contain the water content can be like 50, half of that mass, or 40%. So that's roughly how much humidity is can be found in the biomass, or woody biomass. And the list here mentions cellulose. So that's one of the three main components found in so-called lignocellulosic materials. So basically wood-based materials. And cellulose is the one component that this is separated from wood in pulp and paper industry, and it's the one main ingredient in tissue paper, and for example. Then the lignocellulosic wood or biomass, it contains, in addition, hemicellulose. It's a slightly different material. Cellulose is, we'll take a look at this in a short while. These are both polymeric materials. Cellulose is kind of a linear, made out of just one single monomer, glucose, and hemicellulose is branched, so it's like a tree in a way, that there is this different branches, and those can be made out of several different monomers. So that's quite different from cellulose. Then the third main component is lignin, and that's also made from different type of monomeric materials, but that's more or less like three-dimensional net or network of molecules. So the structure is very complicated, or kind of difficult to define exactly. And in addition to these typical main three components, so you can of course have in biomass, you have more or less proteins. Then you can have extractives, and by extractives it's meant that if you treat the biomass with, let's say, with water, so boiling water, or in any case water, so water soluble components can be extracted out. So those are the water soluble extractables, and part of starch is water soluble. That's an example of water soluble biomass component. Then there are this non-water soluble parts. So if you extract or from biomass, there are this oil or organic soluble materials, and terpenes are a class of those chemicals. Then the ash here refers to inorganic salts, inorganic materials that are in biomass. So sodium, magnesium, calcium, salts and based materials can be found also. But out of these, so what are the most important in terms of making biofuels? So it's of course this cellulose, perhaps the extractives, if you also count the fats and oils, the lipid type materials that are partly or are soluble in organic phase. Also not in biomass production, but of course when humans or animals eat biomass, so they get proteins, which is good source for energy and nutrition and so on. Also some like starch-based materials can be digested by humans and by animals. So that's also like carbohydrates and so on. But in short, so there are chemistry-wise quite a large collection of different types of chemicals, and their relative amounts vary based on the what type of biomass we are dealing with. So this amount of cellulose, lignin, and so on, their percentage varies from case to case. Here, this I took from the course book. So where can you find this biomass? And this is like in relation to fuel production. So of course we prefer to use some waste materials. So agriculture waste, crop residue, also pulp and paper industry waste, or also in some cases the municipal waste or urban waste material. This virgin wood can be of course found in forest products, so basically firewood, trees and different parts of the tree and so on. That is preferred for other applications than fuel, making of fuels, but of course it can be converted to fuels as well. Then there are these so-called energy crops, which can be specially grown for making biofuels. Some of these are also human and animal nutrition, like corn, wheat, barley. You can make alimentary products, and of course you can make also ethanol, which is a biofuel. Different sugars, grasses, woody crops, vegetable oils, and also hydrocarbon plants. And if we last is aquatic biomass, so what grows basically in water. So algae, some kind of weed, and different plants that can be grown in water. And I think the list could be made longer also. There is biomass here and there, so this is not probably a complete list. So few slides about this lignocellulose. So that is this is from the one of the course materials to this review article. So I copied it here for just because it contains quite a lot of information, and the pictures are quite illustrative. So if you see the green material here, so it's biomass. So what it's basically coming down to cellular level. So the biomass is, of course, partly the cell walls and also partly inside of the cell membranes. But the cell walls are often this lignocellulosic material. And if you take a closer look at what the lignocellulosic material looks, so here is a kind of a three-dimensional representation of these different fibers that you can find. So here in the center are these quite straight drawn cellulose fibers. Then these little bit branched fibers represent the hemicellulose matrix. And then here is some not so well defined, but lignin material. The lignin is kind of, somebody refers it's like a glue that it binds the cellulose and hemicellulose together to make the plant be rigid and strong. Here are some representations of these molecules that make cellulose and hemicellulose, and these are different sugar molecules. Cellulose, like mentioned already, it's made only out of glucose. So there is just this one sugar molecule that is combined in the very long line or long polymeric chain. Hemicellulose is made out of also sugars, but there can be 4 or 5 different sugars and in various alignments, so that it has that kind of not linear but branched composition. Lignin, on the other hand, so it's not made out of any sugar monomers, but different types of aromatic components. This not 6-cornered species is a benzene or phenyl ring, so that's the simple aromatic hydrocarbon structure. If you haven't studied chemistry, so just the aromatic structure always should contain these 6-membered rings. Or there are a few exceptions, but let's not go into details. But these are different types of, let's say, basic units that are replicated inside the lignin framework or within the framework. So the lines or arrows from the lignin, so in current, let's say, pulp and paper industry, so let's say that these components are separated from each other or can be separated. So cellulose for paper production, hemicellulose is separated, and it's converted, at least some parts of it, to ethanol, and then the lignin is always separated, and that mostly is burned and made electricity and heat out from that. Often for that particular process, for that processing unit where the pulp and paper industry or factory is working, so they'll burn their lignin for energy. But thinking about the fuels, so in certain fuels the aromatic components are also desired. So lignin could be a good source for aromatic components, because from sugars like glucose or hemicellulose components, you cannot get aromatic monomers or structural units. These graphs are from the course book, and just well, this is nice, colorful representation of that lignocellulosic material. Here it's drawn in a slightly different way, but in any case, so there are these three components. So cellulose, lignin, and lignocellulose, and these three are separated while processing these materials. Cellulose, these percentages vary quite a lot, but cellulose is the main component based on mass, so up nearly half or up to 80% can be the cellulosic material. Hemicellulose 15-13 weight%, and lignin is it's 10 to 25%. And in this graph, this arrow or line continues on here, and it's only displaying basically what can be made out of these components, and cellulose can be broken into smaller monomer units, which is then the glucose. It's a sugar solution. Lignin, the aromatic part, can be broken into these polyaromatic or aromatic functionalities. And hemicellulose, because it's made out of several different sugars, so one can break it into xylose and other sugar components. Crystalline, it's mentioned here that cellulose is crystalline. It refers like the physical shape. So there are crystalline and amorphous materials, and crystalline has this well-defined structure. And that well-defined structure comes from this straight chain cellulose molecules or polymers, which are packed in very, very dense, nice organized fashion, and they form this hydrogen bonds between different polymeric chains. And this crystalline material is very strongly held together. So these bonds are quite strong, and it's difficult to break. And in biofuel section, we would like to break it first of all, to dissolve it to somewhere, and then break all these bonds between the monomer sugar units. But that's challenging because of this well-organized, strongly crystalline or strong intermolecular bonds that are between these different polymeric chains. So hemicellulose, it's mentioned here, for example, it's amorphous. So that is opposite to crystalline. So it's in solid state, for example. Cellulose has this, it's not well organized, or this same structural units are not organized or repeated like in crystalline material. And that makes it also less strongly bound to different polymer chains, and therefore this hemicellulose is easier to dissolve or easier to break also because of this different type of molecular level arrangement.
Mesa, I have a question.
Mm-hmm.
How do they break the crystalline structure of cellulose? With a chemical product, or how?
There are chemical and physical methods. So I think we come back to that when we talk about pre-treatment of lignocellulosic materials. But you can treat it with hot steam or acidic chemicals or something like that, or certain enzymes can also help to break different bonds. So there are, I don't know, I don't remember by heart, but if I say that there are at least 10 or 15 different methods that can be used to break or help to break the cellulose structure. So it's possible, but it's the most difficult more or less most difficult parts to break from the lignocellulosic material.
Okay, thanks.
This table I showed you already, the lower left corner of this material or the table, and here just to compare, we don't need to go through this in detail, but what I want to show about the biomass composition. So here you'll see different types of corn, different types of grass, sugarcane, eucalyptus and pine. This sweet sorghum, I'm not sure what it is, but in any case, so different types of trees and plants, and you'll see that the composition varies quite a lot. So certain are not very rich in cellulose like corn grain, but if you take here, for example, pine tree, so nearly 50% of it is cellulose. So although you can find all these components, so in certain species or certain plants there is a lot of it, and in some plants there can be very, very little of these different components. So if, for example, corn grain, so that's something that you eat, and you'll see that there are extractives. So majority, over 70% of it's actually starch. So it's not terpene, that I know for sure. So it's edible starch that makes majority of that corn. So
sorry, when it talks about energy content, what is this gigajoule or what?
This is energy content is gigajoules per hectare per year. So it's about the productivity when you cultivate it or something.
Oh, okay.
This one, and the BOE refers to barrel of oil equivalent per hectare. So it refers, I think, to how many barrels of oil you can get per hectare out from these plants. So it's basically energy content in a barrel of related to barrel of oil energy content. So, but this is maybe more clear than if you, this is from the course book, so there is a little bit more text in connection to this table number 1. Here is just something on a cellular level. So these sugar or oligosaccharides are components of all the cells, and particularly the cell walls. So, but what are the oligosaccharides then? So I'll show you shortly. But this saccharide is a sugar, and polysaccharide is this chain, polymeric or shorter chain of sugar molecules. So cellulose being one example of polysaccharide. So these are molecules and polymers that are produced inside cells, so part of the metabolism of a cell. And polymeric materials are very common in nature. I just listed some of the typical natural materials that are polymeric. materials. Polymer refers to a very long chain material, and there can be easily, like the chain can contain, let's say, few thousands or even millions of monomeric units. It depends on what polymer we are talking about. But here you'll see cellulose, hemicellulose, lignin. These we have already discussed. All of these are not edible by humans, so human enzymes and digestion cannot easily convert these into energy or valuable nutrition. But starch can be digested by humans, and also protein is a very common polymer. So it's made out of amino acids. So that's the different monomers that make protein polymers. Then you can find silk and wool, like fibers, polymeric fibers, and also this genetic information is stored in DNA polymers. So these are not uncommon in nature. When I talk about sugars, so the name from the chemistry side is saccharide. So saccharide and sugar is more or less synonym of each other. And then depending if there is just one sugar monomer, so it's called mono. If there are two sugar molecules connected to each other, so it's disaccharide. And then if there are three, so it's tri, tetra, etc. If there are already quite many, one can say that it's oligo. And if there are thousands or hundreds of these sugar monomers, so then we talk about polysaccharides or sugar polymers. Another everyday name for sugars, it's carbohydrates. So it comes from the early days of chemistry, when chemists were thinking that sugars resemble hydrates of carbon, although they are not. But in 150 years ago, this was the best they could figure out. The sugar chemistry is very complicated. You don't need to know that, and it doesn't make sense to go through that during this course. It has very little connection to making of biofuels, to go in depth into the different things related to sugar chemistry. But in textbooks, so few things. So the sugar molecules can be in this linear form, which you see on the left hand side here. That is not the most stable or not the most common form of sugar. Only maybe one, in suitable conditions, maybe 1 or 2% of the sugar exists in this linear form, but it's often easier to draw, and it's easier to illustrate sugar molecules in that way. But the more common forms are these cyclic forms of those sugar molecules, like you saw in this picture. So these are 6-ring cyclic molecules, all of these that you'll see on this slide here. And that's the most common form of sugar. And we come back to this a little bit later, but you see here this OH groups. So these are found in alcohol, so-called hydroxyl groups. So the sugar molecule reacts with this aldehyde group and and with an hydroxyl group, and they'll form these cyclic ring structures. And for example, from D-glucose, you can form 6 ring sugars and 5 ring sugars. These 6 ring ones are called pyranose, and 5 ring ones are furanose-based structures. It's all the same glucose, but the 3-dimensional geometry varies or is different. Some examples of these oligosaccharides. So sucrose is sucrose, lactose, and maltose are oligosaccharides. Maltose is composed of 2 glucose molecules. Lactose is broken into glucose and galactose, and sucrose forms glucose and fructose. And quite many of these names are probably common to you. Lactose from everyday life, sucrose or fructose, glucose. These are all sugar, different sugars. And there are, I don't know exactly how many, but if I say that there are thousands of different sugar molecules in nature, so I'm not very far from the truth, because there are a lot of different structures that can be categorized as sugar molecules. Sucrose is one of the most common one. It was here already mentioned that to simplify, it's made out of 1 glucose and 1 fructose molecule by joining them together. And this is the common table sugar that you put in your tea or coffee. And if you hydrolyze it, so it forms glucose and fructose molecules. So this disaccharide structure will break into 2 of those monomeric structures. I apologize, I don't have very many pictures of these molecules because I don't have in my computer this drawing program to make these molecules. I couldn't yet install it. I have some problems with the permissions and so on. The table sugar is most commonly extracted from sugar beet or sugar cane. So when you squeeze the juices out, so those are rich in that sugar component. But of course, again, it's a lignocellulosic biomass. So there are what is left out or left over. So it's typical lignocellulosic materials and so on. Lactose, it's kind of, so at least in Finland, could be called milk sugar. So it's also made out of different monomer structures, so galactose and glucose molecules. Then, like I said, so there are thousands of these, so just few names: raffinose, stachnose, and so on. Sugars that are made out, this is made out of 3 monomers. This is from 4, 5, and 6 monomer units bound together. And basically these can be made out of same sugar molecules or different sugar molecules. So here's one example. Here's the second one. So these drawings are not very nice looking, but you'll see always this cyclic structure connected to another cyclic structure with this type of bond. In this case, there is this oxygen, and that's quite often the bond that is connecting the sugar monomers together. Starch, mentioned already several times, so that is the edible sugar polymer, and if you treat it with water, so there is a small part called amylose, which is water soluble, so that dissolves in water, and majority of called amylopectin, it's insoluble, so although you boil it or cook it in water, so it will not dissolve. And this is common component in our nutrition, so it's common in, let's say, in grains and maize and such kind of potatoes, for example. Here's a representation of these different amylose. That was the minor water soluble component, and here is amylopectin, which is not water soluble. So this three-dimensional structure is more branched here. It's slightly different than the amylose structure, which is quite linear. And this oxygen bridges vary little bit. So this is called 1,4 bond, glycosidic bond. There you'll see that it's slightly different in terms of this 1,6, which contains also the carbon outside from the ring. Here is just oxygen bound to the ring carbons here in 1,6 connection. So there is the oxygen bound to one carbon, and here is CH group in between, and then so that is making those distinguishable from each other. Here are this also, it's little bit confusing perhaps, but there are also these 1,4 bridges, or two different ones. There are alpha and beta forms, and that's not so important to know which one is which, but the cellulose one, this is drawn now in quite nice way, that it shows that this cellulose structure is really nicely linear, but in starch the 1,2 linkage, it's not linear. So if you would continue this structure, so if it would not, you cannot put it in a linear way. And this is one part, partly the reason why this cellulose is not really easily breakable, and it's not soluble in water because it's linear. It on a molecular level it packs very densely and bounds to each other strongly, as discussed already. But if you have this kind of curvy or somehow irregular shape, so this packing is not that regular and strong. So therefore, water molecules can penetrate between these chains and make it at least partly soluble in water. Here is something about cellulose. I think there is nothing new that I haven't already mentioned. This is one picture representative or representing cellulose, this kind of that three-dimensional structure. So here are these interchain and intrachain. So these two neighboring monomer units can be held together slightly at least between these hydrogen bonds. So there is hydrogen bond marked with these dotted lines. And then you can have these bonds also between neighboring chains, and you can also have those similar bonds between, like on top of each other, remaining these sheets of cellulose and so on. So there's lots of bonding to different directions, and that makes it very strong, the material. I think this is more or less the same what we have already seen. So linear chain of one short part of cellulose polymer. Then we come to lignin, and this picture is in the course textbook. I took it from there, and if I remember roughly, so although it has been studied, so the actual composition of lignin, it's very difficult to figure out, or one can say that it's not fully characterized or known yet. But like mentioned, so there are these certain aromatic structures that are repeated and bound to each other. So lignin forms this quite complicated, more or less three-dimensional network of molecules. So this is very large and complicated molecule monomer network. Took this picture again because here on the left-hand side you'll see some of these building blocks or repeated units. I think I have another picture about it also. So it's this one. This term heterogeneous polymer, it means that it's made out of several different monomers. And this coumaryl alcohol, coniferyl alcohol, and synapyl alcohol are some of the structures that can be found in lignin. But if you are able to break the lignin into these smaller units, so here are quite good chemical functional groups: aromatic ring, double bonds, alcohol, this methyl, what is this? Hydroxyl group and so on, that can be converted to different chemicals. So that was about lignin. Then the third and last component in the mixture is hemicellulose, and that's again heterogeneous polymer polysaccharide. And this is really lousy picture, sorry about that representation of hemicellulose, but what you should see in it, so it's made out of different sugars. So these different colored 6-ring structures refer to different sugars. Also that it's not linear, but there are branches of these. So it's more complicated, the structure. And the side chains, so if there is a longer main chain, so there are side chains made out of different sugars like xylose, galactose, and fructose. Arabinose can also be there. So some of them are 5-ring sugars, some of them are 6-ring sugars. And part of hemicellulose can be slightly more easily broken out from this lignocellulosic materials. So it can often be removed in the pre-treatment step of a woody biomass. So hemicellulose part can be separated first, then you are left out with cellulose and lignin, and then those can also be separated from each other. And in pulp and paper industry, cellulose goes for making the paper, and hemicellulose has been a side product, but at least in some pulp and paper related processes, so these sugars are hydrolyzed and converted to ethanol, the hemicellulose part, and the lignin, like said, so it's a source for energy. It's burnt for making of electricity and heat for the processes. But the lignin structure is nowadays, or has been for last 20 years, it studied quite a lot, so that it would not be only burnt for energy, but the lignin components could be used for making, for example, chemicals and different fuel components. Hemicellulose, according to some sources, so it's a shorter chain structure than cellulose, and also because of the branching or branched structure, so it's therefore easier to dissolve and separate from the woody biomass. That's from that molecular level explanation. I think we'll take a 15-minute break before continuing with these triglyceride structures. So next, something about triglyceride producing plants. And triglyceride is coming back to this same table material. So it's of course majority of biomass contains some amount of triglycerides.
Sorry.
But yeah.
Are you sharing?
Oh, you don't see anything?
No.
No.
Okay, I'll try again. I was just a moment. constraints. Okay, can you see now?
Yes.
Okay. Yeah, so triglyceride refers to this biomass that is rich in these oils and fats, or fats maybe refer more to animal-based biomass, but this oils more to this plant-based material. In any case, so this what is the composition of a biomass? So the oil, fats and oils and triglycerides are just one part of the plant material. More or less all biomass contains it, some very tiny amounts and some very large amounts, and I think those that contain large amounts are typically these oil producing plants, like so. So again, keep in mind that the biomass is mixture of different things, although it's grouped in this way as in the textbook, so that we have this triglyceride producing plants. Okay. Chemically, triglyceride is esters of glycerol or fatty acids esterified with glycerol. So the fats and oils, at least according to some source, fats are considered solid at room temperature, and oils are in the liquid state at room temperature, but this is not a very chemically exact definition. So you cannot, like, by looking at the molecular structure, say for sure that this is fat and that one is clearly oil. So it refers to physical properties. What's the melting point of that particular material? And these fats and oils are very rich in energy, so therefore it's kind of as such already works as a fuel in some parts, but the fuel properties can be notably improved by modifying these chemically, and that's something that we take a look at later on during this course. This is how it looks in the structure, and you'll see here this there are these, every triglyceride contains this glycerol part, so it's these 3 carbons here with the hydrogen. So this has been an alcohol, and there was hydroxyl group instead of these, so it was triol, 3 hydroxyl group containing alcohol originally, and that reacted to form esters with so-called carboxylic acids, which are long enough so that they are called fatty acids. So there is chemically 3 ester linkages or bonds between an alcohol and 3 fatty acids, and in nature you can find triglycerides that have the same fatty acid component, or these 3 can be different ones. So that brings the differences between different fats and oils, like the chemical differences in these fatty acid parts. The rest of the molecule is totally the same in all the cases. So basically there is glycerol part and 3 fatty acids that has been esterified in that structure. Quite simple in principle. Okay. I didn't know that here are these animations on the slides. Strange. Yeah. So what is a fatty acid? So if you have studied a bit chemistry, so there is a fatty acid is basically a carboxylic acid. But what makes it fatty acid, or it's just that it's found in these fats and oils often, and it's usually these quite long chain carboxylic acids. So this right hand side part is COOH part, that's found in, it's a carboxylic acid group, and then this zigzag structure is just hydrocarbon chain, and it can be very short or it can be very long, and everything in between. Generally, when we talk about fats, so if you have a saturated fat, so it doesn't have any carbon-carbon double bonds, and unsaturated fat can contain one or multiple carbon-carbon double bonds. And the saturation tends to increase this melting point, so that these are more or less solid at room temperature. Okay, unsaturated versus saturated. So said already, multiple double bonds, or at least one or multiple, and that similar like with this sugar polymers. So this double bond makes the fatty acid tail a little bit like twisted, so that the melting point decreases and it remains liquid at room temperature. Typically vegetable oils are these unsaturated ones, and saturated fats can be found in animal fats. So structurally these are all the same triglycerides, but the fatty acid tail part varies. If this would stop rotating, so you would see examples. So these often have this, it's not a systematic name, so fatty acids tend to have these special names for themselves. So here are a few saturated ones, so no double bonds, like stearic acid, palmitic acid. And unsaturated fatty acid, here is monounsaturated, here is polyunsaturated, with several, here up to 4 double bonds in that fatty acid part. Here is again example of real life fats and oils. So you'll see animal fat, vegetable oil, corn oil, vegetable fat, and so on, sardine oil, beef, olive, corn, etc. So how they vary, so the fatty acid parts are different, and in real life vegetable fats and oils, you'll see that what different types of oils there roughly are, fatty acid parts there roughly are, and that basically makes their different chemical and physical behavior, as the rest of the molecule is totally identical. So olive oil here so has quite a lot of oleic acid, monounsaturated, but for example, here coconut oil has only very small part of oleic acid based structure. So okay, the degree of saturation, we already mentioned this, but if there is one double bond, it's mono, and if there's more, so it's polysaturated. And here you'll see how the melting point changes. So if you have one double bond, it's a bit higher. Second one decreases it, and third one decreases it even further. This illustrates the difference in the geometry what I mentioned. So this is just the fatty acid, carboxylic acid part. So when it's unsaturated, it doesn't have any double bonds, so it's this quite linear structure. When you form one double bond, so in that double bond part, it tends to twist like this. If you have more of them, so you'll see that it becomes even less linear. And this is making it also melt at lower temperatures because it doesn't pack so well compared to this one. Why is this showing again? And the table from our course book also describes chemical composition of different vegetable oils, so the fatty acid composition. So just what the previous pie chart also represented. So there are different fatty acid compositions, different amounts of those, and that makes the particular fat or oil, or gives the common properties to it. I think, well, I don't have so more about these triglycerides. Okay. I guess that's then. Last, or not last, but next group of biomass, let's say, components are terpenes. I mentioned that these were the part of the extractives, meaning that if you treat the biomass with organic material, some organic solvent, so the terpenes tend to enrich in the organic phase, out from that biomass into the organic phase. If you treat the biomass with water, so then you get water-soluble extractives. When we treat it with organic material, so we get organic soluble extractives, and terpenes are one type of biomass chemicals that are this soluble to organic matter. And here it's in this table just means grouped all together, but it's again there are like hundreds of different terpenes that you can find in natural products. Similarly, as also sugars, there are hundreds or even thousands of different sugar structures. So terpenes are made out of these basic building blocks. So these C5 isoprene units. So what you'll see here, it's basically hydrocarbon. Fuels tend to be hydrocarbons. So these are quite nice components for fuels. There are these double bonds that you can react with something, or you can remove them by treating with hydrogen, for example. But these are components that could be nicely used in fuels. Here are some examples that the C5 unit, then when those combine together a little bit in a similar way, like with sugars, there were monosaccharides and disaccharides, trisaccharides. So if you combine these units together, 1, 2, or 3, so you get these different more and more complicated structures, but these will not form, let's say, polymeric structures. That this you will not find these terpenes made out of hundreds or longer isoprene units. So these are reasonably small molecules. Also, one can find not so self-evident that you'll see this C5 repeating unit, but these are also terpenes. And for example, limonene, pinene, menthol, geraniol. These tend to be quite valuable molecules in that sense that these can be used in fragrances and can also be used as solvent in industry. So if one is able to separate these, maybe these have more valuable use elsewhere than in the fuel sector. But I have experience from another project that we were using limonene, and it has very this lemon-like pleasant smell, and it's extremely good solvent. So it can dissolve even some plastics and so on. So that one application is that it's this kind of cleaning agent if you really want to remove difficult stains. So that's good for that. Here are examples of some larger molecules made out of these terpene units, but like I said, so one cannot say that these would reach this polymeric lengths. So these are just large molecules. If you have heard about rubber, natural rubber, so it's also made out of these terpene materials. And here this polymeric or this chain is more or less represented. And if you vulcanize or make this synthetic or rubber, so you'll generate this sulfur linkages between these different chains. This makes it mechanically much more stronger, much more usable, this natural rubber. I think this is not very much used anymore at this in car tires or in rubber-like materials. So those have been long since replaced by synthetic rubber and synthetic plastic rubber-like materials. last what textbook will include in that biomass is algae, and I don't have so many slides regarding this, but some 20 years ago this was a quite hot topic in connection to liquid biofuels. So companies and research projects were studying quite a lot how to produce, in particularly microalgae, and how to extract the hydrocarbons, the oils out from these algae materials. Typically, there is microalgae. These are very tiny microscopic organisms in connection to macroalgae, that is more or less this seaweed that is easily visible without any microscopes and so on. The good thing and interesting thing in algae is that its growth rate is quite fast, so it really grows rapidly, and also it produces large quantities of these triglycerides. So if you can extract them or remove them from that algae material, so it seems like a good source for the oil to make, let's say, fuels and so on. But I remember that this algae growing was quite challenging. At least quite many projects failed to make it so that it would be economically feasible or commercially viable, let's say. I don't know the current situation, if some companies are producing triglycerides based on algae. This is a composition of certain microalgae, different species, and here you can see the triglyceride content: protein, carbohydrate, glycerol, and also some components, unknown components. So if you just compare this simple triglyceride composition, so here are fairly high levels of triglycerides, like over 50% or close to 50%. And that looks or seems quite high if you compare. I don't have now table, but these oil producing plants, so it would be interesting to compare how much different coconut or rapeseed or olive contain triglycerides. That can be found in the textbook, but I haven't the info here at the moment. But algae can be also, of course, not just to making of oils, but one can also make reasonable amount of protein. Protein is not really interesting for making biofuels, but of course it's a higher value added product in terms of it can be nutrition for us humans or animals. So that is also potential for that. And carbohydrates, similarly like in other biomass, so can be found in the algae. I had some slide there that mentioned the functional groups, and if you take a look at these different biomass components, so the cellulose and hemicellulose are made out of sugars or carbohydrates, And there are typically these hydroxyl groups and aldehyde groups, and also this ether linkage or ether bridge, this carbon-oxygen carbon bridge. Then the triglyceride part, so there one can find this ester linkage. If it's unsaturated, so you can find carbon double bonds. And in principle, well, there is not really OH group, but it has been made from this alcohol. And then the lignin, the different thing compared to more or less rest of these things are the aromatic rings that can be found in lignin. Otherwise, there are similar linkages as in these other terpenes, are hydrocarbons that contain carbon-carbon double bonds. And last but not least, so the algae, it contains basically more or less all these ingredients, so then it has also the same functional groups. And why I'm talking about these functional groups is coming in the next part or next slide set. So basically we can predict how these components react, or what type of products we can maybe make from these materials. So